Hi, everyone. Thank you so much for joining us for the Understanding UEFI and PI Architectural Events as part of the UEFI 2021 Virtual Plug Fest. We'll get started in just a few moments. Thank you. Hi, everyone. Thank you again for joining us for Understanding UEFI and PI Architectural Events webinar as part of the UEFI 2021 Virtual Plug Fest. I want to take a moment here to introduce our presenter. So we have Felix Polodov, who is the Director of Firmware Core Architecture at AMI. And I will go ahead and pass off to Felix now.
Hello, everybody. So before jumping into the subject, let me briefly explain why I decided to pick this particular topic. So after all, the UEFI events are discussed in one of the first chapters of the UEFI specification. So chances are, if you ever gave a New Year resolution to read the entire UEFI spec, most likely you reach at least up to that chapter before giving up. However, there is a lot of small details related to events. First of all, the spec evolves, so the content changes. In fact, there were a couple of events just added just recently in the UEFI 2.9, and before that, I believe in 2.8 errata, there were some clarifications added regarding usage of some events. So contents keep evolving, and then also it's not focused in a single chapter, like I have some references to sections of the spec, but the full story, the full picture of dealing with events is more complicated. For example, like exit boot services event is described in chapter 7.1, but some usage rules are described in a different section in the core in the exit boot services section of the specification. And then, of course, there is entire PI specification that adds quite a lot of information about events. So that's why I thought it would be useful to give to try to present this whole picture of event architecture in UEFI, maybe to show the relationship between events that may seem unrelated because they're defined in completely different parts of the specs, or sometimes in a different specs. There is also a practical aspect. There are errors in dealing with events are typically very costly. They're typically very difficult to debug, and then as we discuss, I'll highlight some of the pitfalls or corner cases when developers have to be careful and cautious. So I am not, so this presentation is not meant as a UEFI tutorial. So as I said, I assume most of the people do have some at least basic understanding of what UEFI event is, but I'm still kind of presenting in a short form some basic information so that you can understand the rest of the presentation. So even if you are not familiar with the events, there will be enough context in the presentation for you to understand the presentation, but don't assume that you don't have to go back and read this back. So event is a callback-based binary-to-binary communication mechanism. So it's similar, so every operating system has an event object which is used for inter-process communications. Obviously, in a firmware, you don't have processes, environment are much simpler. So the same concept that exists in most operating systems was adopted to the UEFI environment. And then, of course, since we don't, there are no, UEFI is not a multi-process, not a multi-threaded environment. So the event was adopted to exist in a single-threaded UEFI environment. And there are boot services that can be used to create signal events and so on. We'll see how it works in later on. So essentially, as I mentioned, so that's events is a communication mechanism. It means there are at least two parties involved. So typically, there is an actor, so somebody who detects an underlying condition, and then there are reactors. So it can be one or multiple drivers that want to perform certain action when event happens or when event is signaled in UEFI terminology. The UEFI events are defined obviously by UEFI specification, but PI specification has a similar callback mechanisms, a bit simplified callback mechanisms that are also defined for the PI and MM environments. And also PI specification extends list of standard event groups that are part of UEFI specification. So before proceeding any further, I would like to clarify a few things. So you've seen on the previous slides, I've used, I refer to UEFI specification, PI specification, then I mentioned UEFI events, but then said that PI specification has something similar. So let me explain the terminology I'm using. So UEFI and PI are two different specifications managed by the UEFI industry group. UEFI specification defines interface between firmware and operating system. There are many different ways to implement UEFI firmware. PI specification, which stands for Platform Initialization Specification, it defines one possible way to implement the UEFI firmware. So as of today, that's the mainstream implementation. Probably that's the most popular implementation, but that's not the only implementation. So why it's important for you to understand the difference between those two specifications? Because when as a developer, when you write your code, or you have to understand which interfaces, which API is available to you. What is your scope? So if your code is targeted for the PI environment, essentially this entire ecosystem of PI and UEFI is at your disposal. But if the goal is to be strictly UEFI compliant and not necessarily depend on details of UEFI implementation, then you should stick to UEFI interfaces only. So typically there is like a simpler rule. If your code will reside in the in that flash chip that sits on the motherboard, and if you know that it's going to be API implementation, then you can deal with the API code. If you are writing an OS loader or an option ROM that will sit on a plugin card, then to improve interoperability, you typically would want to just limit yourself to UEFI interfaces. Although, as usually, there can always be exceptions and special cases. So in the presentation, I'm covering both domains, the UEFI and PI, but I try to make it clear when I'm referring to UEFI and when I'm referring to PI. So it should be so that specification, the presentation hopefully will be useful to people who just interested in UEFI and to those who code for PI implementation. Events. So obviously, entire specification is about events. So I use term event in a broad sense. So, like, there is a chapter 7.1 which describes UEFI events, but as I mentioned, PI specification also has a similar callback-based mechanism. So when I'm saying event, I imply callback-based mechanisms, whether it's a UEFI or PI. But when it's important, when there is a difference in behavior, I'm explicitly clarifying whether I'm talking about UEFI events or I'm talking about events in general. And then finally, MM versus SMM. So MM stands for management mode, and then SMM, system management mode. And those terms, if you will be talking to people from the industry, you may hear both, and there is sometimes different people have different interpretation of the terminology. So I would like to clarify the usage of the terminology. So from the spec point of view, these are essentially the same thing. So if you look at the older revisions of the PI specification, management mode environment is referred to as SMM. But in the latest version, it's almost exclusively MM, but SMM may be used in a few places. So essentially, originally, as you probably know, SMM is a technical term on Intel architecture. So the spec begins from the Intel specifications. So as SMM was used as a natural reference to the Intel architecture. But as specification evolved and became more generic and covered more architectures, the spec was updated to use MM as a more architectural neutral term. But as I said, in a few places, SMM is still used. So essentially, from spec point of view, these are the same thing. However, when you will be talking to people, you may hear different usage of the terminology. Like some people use SMM to refer to specifically to MM implementation on Intel architecture, and MM to refer to MM implementation on ARM architecture. Also, specification defines two possible implementations of the MM environment, so-called traditional MM implementation, traditional in a sense that it was there first. When MM environment is initialized during DXC phase, and there is an MM driver can, during initialization, use boot services. And then a so-called standalone MM implementation, when there is like a partition between Dixie world and the world. So sometimes is used to refer to a traditional implementation, and refers to a standalone implementation. So when you talk to people, you may want to clarify explicitly what they mean. What I mean in my specification, I'm just referring to as a generic term used by the specification. UEFI events are used for different purposes. So I'm trying to list the kind of largest functional classes of the UEFI events. There are UEFI events is a generic mechanism, so any driver can use events for their driver-specific, to implement driver-specific logic. So these are private events. Then UEFI specification defines a service, event-based service to register callbacks on installation of a certain protocol. So these are called protocol installation notifications. Some protocols use events to implement protocol-specific logic. For example, network protocols perform a lot of background processing, so they use events to notify the caller that certain task has been completed. And then the simple text input protocol drivers use events to pass the information that the keystroke is available. There are timer events. Essentially, this is a UEFI polling mechanism. As you know, UEFI is not interrupt-based, so polling is a mechanism that can be used to, for example, serve device requests. It's possible to create a one-time timer callback or a periodic callback, and events is the machinery behind the timer implementation. As I already mentioned, there are protocol installation notifications. PI, these are defined in the UEFI spec, but PI specification defines also a similar simplified protocol installation notification callback mechanisms for PI and environment. And essentially, this mechanism is used to implement events in PI outside of UEFI domain. There are also system events. Those are events defined in the spec. They have system-wide special meaning, and there is one important subclass of system events. These are boot flow events. These are events that signify a certain stage of the boot process. So I couldn't resist my chance to use animation, so here it is. Just a brief overview of how UEFI events work. So the spec defines two types UEFI events. Events notify on signaling. So the event actor, once it detects the event condition, it calls signal event UEFI service, and then whoever is registered for that particular event gets notification in the form of callbacks. That can be one or multiple reactors. So if you've seen on that animation, the callbacks were dispatched one by one. So UEFI specification defines priority levels for the callbacks. They're called task priority levels, or TPLs. So there is a TPL callback, TPL notify, and TPL high. So the callback is the lowest TPL level, so it's kind of the default. If you don't have special reason to use elevated TPL, you should use TPL callback. TPL notify, and then TPL high. TPL high is reserved for use by the firmware. What does it mean? It means, first of all, that UEFI drivers should not use it. It can be used in the PI domain, but use with caution. So on TPL high, interrupts are disabled, which means timer interrupt is disabled. So by executing a lot of code on TPL high, you may break certain timer-based services and degrade system performance. Events are created using create event or create event X service, and create event is primarily used for binary to binary notifications, and create event X for broadcast events. Like on this picture, we have a single driver that signals event and multiple consumers. And second type is notification on wait. So a driver may call check event or wait for event a UEFI service, and once this happens, callback function in the actor driver is invoked, and then the driver can check whether underlying condition occurred or not. For example, whether there is a pending keystroke or not. And if it is, it calls signal event, and then the reactor gets the event status. So most of the events that we will be discussing today are of type notify signal. They are used to implement all those system events. So PI specification has, as I've mentioned, a simplified callback mechanism. Drivers who wants to get notified will call special API to register callback on protocol PPI installation, and then when the interface is installed, the callbacks are invoked. There is no priority levels in the PI world, with one small caveat that we will discuss in a minute. So some practical guidelines on event usage. Don't forget that your code may be interrupted by event callbacks. As I've mentioned, UEFI is a single-threaded environment, but there are timer callbacks. So there may be reentrancy unless you use certain protection mechanisms. The protection mechanisms are essentially UEFI TPL API. It may seem that your driver, there is no context for your driver to be called by the callbacks, but essentially you never know. Like, for example, USB is a hot pluggable bus, and you can have all kinds of UEFI devices. It can be a keyboard, a monitor, a mass storage. So, for example, a partition driver can potentially, they can be potentially reentrancy in a partition driver or in a console splitter when USB device is hot plugged. And it's really difficult to debug those events. Those errors. So it's just better to be safe than sorry. In the same lines, never break TPL restrictions defined in chapter 7.1, table 7.3. As I've already mentioned, you should use the lowest TPL possible. Essentially, if you don't know why you're using higher TPL, you shouldn't use it. And for the protocol installation notification callbacks, don't use them if there are more appropriate mechanisms. Like in the UEFI world, sometimes people use callbacks, protocol callbacks as a surrogate to UEFI driver model. The UEFI driver model is a more advanced mechanism. It should be used when appropriate. And then, of course, there are dependency expressions. If you don't need a dynamic behavior, if functionality of your driver starts after protocol is installed, then you can just use dependency expressions. So there are a few system events that are defined by the spec. Memory map change event, reset system events. Those events are not currently fully implemented by the IDKit 2. This is just for your preference, so that maybe it will save you a few hours of debugging. PI DXC dispatch event is actually used for internal communication between DXC and MM Foundation. Typically, you won't have to deal with it. And then the boot flow events. Those are the most interesting events. Let's take a closer look at them. So here is the events that happen in PI. So I assume that this is like a time diagram. So the reset is at the top, and then we are moving towards boot to OS, which should happen like at the bottom. The master boot mode PPI, which is installed when platform boot mode is detected. Memory discovered, there is a bit of confusion with the name, and it is also known as a permanent memory install PPI, or just sometimes it's called memory install PPI or install PI memory. This is because in the spec, actually itself, the different names are used, but it's the same event. And the end of PI, which is triggered as the very last thing in PI. A few things to note. So all the PI events can be used as a callbacks or as a dependencies. Master boot mode PPI is typically installed prior to memory discovered PPI, but not necessarily. It can be, the spec, there is no spec requirements. For example, there are some implementations when memory discovery happens before PI. So when PI firmware is launched, we already have memory. So the memory discovered PPI can be installed like almost immediately. So just always explicitly list your dependencies. Don't assume anything. And then, of course, recovery mode PPI can be installed at any point because recovery can be triggered by user pressing a recovery button or by firmware corruption, so it can happen at any time. Also, PI specification actually defines two different notification types. The callback notifications and dispatch notifications. Dispatch notifications, if you look at the code, they're barely used. But I think there is, in general, they should be used more. There are at least two reasons to do so. So originally they were, so the key difference, the callback notifications is invoked immediately when the PPI is installed. So before returning from the installed PI service. And then the dispatch notifications are deferred until entry point of the PIM that installed PPI returns control back to PI Foundation. So originally, dispatch notifications were created to optimize stack usage. In case of callback notifications, we are creating nested stack frames. So the PI Foundations calls PIM that installs PPI, and then in turn, we are calling all the callbacks that registered notification. So dispatch usage of dispatch notification allows to optimize stack usage, and then also, which is stack overrun is not a typical problem thanks to hardware advances. Typically, we have enough space, but we do see that happening on occasion. First of all, the cache's RAM has its limits, right? And then even after memory detection, PI is typically using just a portion of system memory. So on special boot pass, on S3 resume, when you have limited amount of available memory, or on special boot configurations like in recovery boot mode, when you load in your entire capsule into memory, you may still run into, essentially you may still run out of memory. And then that debugging is very difficult. It may take, literally days for you to debug it or even reproduce the problem. So I would say usage of dispatch notifications should be a good development practice. And then dispatch notifications can be used as a control flow tool. Essentially, dispatch notifications are guaranteed to be invoked after the callback notifications. So you can use callback and dispatch notifications as two priority levels for in the PI world. Dixie BDS and runtime. So there are quite a bit of events. Essentially, if you see, there is a bunch of events that are kind of drawn together. So these are event pairs. So this is a technique or design pattern that is used by UEFI and PI specification in multiple places to simplify transition between two phases, so provide enough flexibility for transition between the sections, between the phases. So the first event typically presents the last chance to access system interfaces or to change system configuration before the transition. And then the second event can be used by handlers that facilitate the transition and by handlers that need to see the finalized pre-transition configuration. If it sounds a little bit abstract, we can look at specific examples in the UEFI specification, which defines three such event pairs. So end of Dixie and MM ready to lock. So the end of Dixie presents the last chance to use services that are about to be disabled and to modify hardware state that is to be locked. For example, if you want to, there are certain UEFI variables that may be locked. So this is the last chance to update them. And then MM ready to lock, this is where the actual transition happens. For example, when the SPI chip is locked for writes outside of MM. Also, MM registration stops at that point. So if you are writing a code that disable certain services that performs platform hardening, you should install your callbacks on MM ready to lock, not on end of Dixie. And the other way around, if you want to use your the service that is about to get locked, you should use first event from the pair, end of Dixie in this case. Yeah, otherwise you will be depending on the order of callback execution, which is not guaranteed, which is not defined by the spec. So there are also ready to boot, after ready to boot, and before exit boot services, kind of similar. The idea is similar. Exit boot services, you have to be extra careful with that event. Because according to the UEFI specification, it's you cannot use any services that alter memory map in the exit services callback. But the problem is, if you use service outside of your driver, you have no idea whether it's altering or not altering memory map. So essentially, potentially, any usage of any boot service can violate the spec. So if you must perform interaction with the other driver, you should use the new event before exit boot services that was introduced in UEFI 2.9. So just a few things of notice. So the end of Dixie event, despite its name, can actually happen during BDS. The spec defines end of Dixie as the last chance, as the event is triggered before third-party code is about to get executed. So, but potentially, if you have onboard devices, it's legal to connect them before the end of Dixie. And then the ready to log, the technology evolves. So nowadays, is logged typically way before that event actually is generated. The relative order of PIA, DXC, and events is not defined. So, for example, Dixie ready-to-boot handlers may get invoked before or after ready-to-boot handler, or it can be some can be invoked before and some can be invoked after. Don't assume any particular sequence. Ready-to-boot and exit boot services happen after ready to log, which means they are outside of the trusted platform boundary. So your code should work, should treat them appropriately. First of all, they may never happen, or they may happen, but the data that you're getting from outside of may be spoofed or incorrect or corrupted. So just be careful in those event handlers. And the ready to boot event is generated whenever we are trying to boot. So it can happen multiple times if you have multiple boot options. Virtual address change happens at runtime. So once again, relative order of callback handlers is not defined by the spec. So if you are calling runtime service implemented by another driver, it may or may not work, because if callback function of the driver you are calling executed before you, then maybe the driver has already converted to use virtual address map, and it may not work as intended. So be careful in those events. So this is it. Thank you for listening, and I think we are ready. If there are any questions, we can cover those.
Great, thank you, Felix. So we do have one question here. How do I specify, for instance, that I want to be the very last driver called back on any given event?
So you don't. So the UEFI specification does not define relative order of execution of callbacks. So there are priority levels. So there are essentially two groups. So some ordering is possible. But if you absolutely must be the last, there is no spec-defined mechanism for that. So in your private implementation, if your handler has to be called after other handlers which are also developed kind of by your company, you can create a protocol and just use protocol to explicitly give control to your handler, or introduce another event and then that is signaled at a later time. But there are no generic mechanism to be the last handler, and this is intentional because it's all about collaboration. It's all about ecosystem. So if such interface would exist, I'm sure there would have been more than one party to that wanted to use that service. And when code comes from multiple parties, sometimes even in binary format, such unique services where only one actor can get serviced, are asking for troubles.
Next question is, you mentioned boot service functions can be called EBS. What does that mean and how?
Boot service functions can be called what? Can you repeat this?
You mentioned boot service functions can be called EBS. What does that mean?
Boot EBS. Trying to see where I might have mentioned that.
Oh, exit boot services, perhaps?
Oh, exit boot service. So the yes. So for example, Redfish specification says that special end of session command has to be sent to BMC at exit boot services, or UNDI driver needs to shut down to perform certain steps to get ready to stop periodic polling of the server, or your NVMe driver may need to do some flashing of the cache content to the device. So there are some practical reasons to use boot services at that point.
Great. Last question here. Why in exit boot services event can we not update the ACPI tables or SMBIOS table? What happens internally?
Yes. So it's not about implementation. Implementation can handle any usage of the services. It's about contract between firmware and operating system. Of course, when control is transferred from firmware to the operating system must have up-to-date memory map. And that transition contract is defined by the UEFI specification in the exit boot services chapter. So it works like this. Before invoking exit boot services, OS must call get memory map. And get memory map returns a key, which is a unique number that represents current memory map. And this key is passed into exit boot services service. So, and then firmware validates. It makes sure that OS indeed has the very latest memory map snapshot. So if exit boot services event callbacks alter memory map, essentially call to exit boot services fails. The UEFI specification has a provision, for that. It says that if a call to exit boot services fails, OS have to repeat the sequence. It has to call get memory map and exit boot services again. So there is some recovery mechanism, but in general, this is essentially the main reason to limit modifications to system environment in the exit boot services callback. Also, exit boot services callback are used to shut down drivers functionality. So when you call certain service, you don't know, maybe it's already transitioned to runtime execution mode. So the situation improves with introduction of the new event in 2.9, but in general, you should be careful. For example, if a CPI table exists, maybe you can update it without touching the memory. But then again, the spec doesn't define at what point OS consumes ACPI or SMBIOS tables. So potentially OS may have already parsed them, and then your changes will not, get reflected.
Great. So that's actually the last question we have time for. if you folks want to join us in the WebEx Q&A, we will be moving there right now. Additionally, just to note, these slides will be available on the UEFI Forum website. So thank you all so much, and we will see you in the live WebEx Q&A. Thank you.